Hello everyone, I'm Frank and welcome to Frank Puzzles, and this is today's easy level puzzle. And take that easiness with a grain of salt because it's considered easy by the people on the Logic Masters Germany forum, and there's a lot of smart people there. Today's puzzle is called Bonsai by Michael Lefkowitz, and here are the rules. We have Latin square rules where we need to place the digits 1 through 5 once each in every row and column. We have tree growth, where from one or more of the roots shown in the grid, we need to draw brown thermobranches along which digits increase from the root. And diagonal movement is allowed, as is branching. So basically, from these cells here, there must be cells that increase from the root, which is here, to wherever the branch goes. And you can go diagonally. So from one of the more brown thermobranches. So if you have increases in these digits, then they must basically go up as brown. We don't have brown really. I guess we have orange as the next best thing. So we have brown, center. That can go something like that. And it must be increasing constantly from this cell. So that's how the tree growth works. We have yin-yang, where we need to color the root and branch cells brown and the rest green. And each color must form an orthogonally connected region. That is, no 2x2 area can be all one color. Interesting. So the branches and the roots are brown. I guess we'll make it orange in this case. And the non-branches are going to be green. And So basically, I guess if this digit is greater than both of these two, you would have to draw branches to that from the root. That's kind of interesting. And say this was greater than both of those, then you would drop these two. Say these two were greater than this cell. So say we had something like this was, I don't know, 1, 2, this would be 3. Then you would have like 4 and 5 there. And then you could have something like this along the as the bonsai tree, or the roots and branches. And the brown region, which is the roots and branches, must be an orthogonally connected region, and so is the green region, which is everything but the roots and branches. I've got a spider here. I'm gonna pause. I'm gonna get the spider first. Sorry about that. There was just a spider just came straight down from the ceiling, and it was just like came right in front of my vision. I was just like, oh, what the heck is this? Anyways, I guess we have some spiders in our bonsai tree. Right, so yin yang. All the roots and branch cells are brown, and the rest must be green. And each color must form an orthogonally connected region, and no 2x2 area can be all one color. So as an example, we could have something like this, which is all brown, and then these are all green. And this would be a valid yin-yang shading, because all the brown cells are orthogonally connected. And what does it mean to be orthogonally connected as a region or as an area? It means that you can go from any cell in the brown region to any other cell in the brown region just by going through edges, all while staying within the region. And the same thing is for the green region. This would not be a valid coloring because for the green region, you cannot go from any cell in the green region to any other cell in the green region just by going through edges while staying within the region. You'd have to go through a corner here, or you would have to go through an edge, but then get outside of the region to do so. This is also not valid because we have a 2x2 area that is all green. And you can't have a 2x2 area that's all green or all brown. So if this were brown or orange in this case, this would not be valid as a yin-yang shading because we have a 2x2 area that's all brown. And that's an example of how yin-yang works. We also have crop key dots, where digits separated by a black dot are in a 2-to-1 ratio. So for example, if this were equal to 2 here, this would have to be 1 or 4 to maintain the 1-to-2 ratio that's between them. And those are all the rules. If you like to play along, there's going to be a link in the description. And now, I'm going to get started. Let's... Oops, whoa, what the heck happened there? Oh, info, right. Let's go. Okay, so to be in a 1-to-2 ratio, we have this 1, 2, and 4 here. The only digits in a 1-to-2 ratio between 1 through 5 are 2 and 1 and 2 and 4. So we're guaranteed this is 2, this is 2. For each of the roots shown, draw brown along which digits increase from the root. We know these are brown, obviously. How does this work? Well, we know, okay, so we know one of these areas must be brown here. And it could be all the way here, or it could be all the way here. I don't know if we have... Can we go sideways? I don't think we can go sideways. That doesn't seem to make any sense, right? Oh, you can't really go sideways. Well, I guess you could go sideways. The thing is, it must be consistently increasing from there, right? So... even if we go that way, the problem is we need something going this way, right? We know, okay, one of these two has to be greater than or equal to both of these, or all three of these, I guess. Hold up. One of these has to be, so one of these has to, so we either have green, brown, green here, or brown, green, and then that could be green or brown, right? Or I guess these could be green and green. So the remaining digits in this row have to be 1, 4, 3, 4, 5. Same with this row. We have to get brown everywhere in every 2x2 box. We also need green everywhere in every 2x2 box. So at least one of these is green. Um, hmm. So the thing is, you can only go from these cells to these cells by always consistently increasing. So for that, you would have to go at least, to get to the first row, you would have to go 5, 4, 3, 2, 1. So for one thing, we know then that 4 of the cells have to be green in column 5. And it could be all 5 cells are green in column 5. But 4 of them are at least green. So we know we have some greens here. We also know, okay, so in a yin-yang shading, the edges can only swap colors 0 or 2 times. And the reason why we know that is, say what happens if we have, well, we can't have a change of shades once, because it must change back to the other shading, right? So if we have green here, we can't change once and then not change again, because that it doesn't work, right? It changes from green to brown here, and then it must change from green to brown this way. But we can't have more than 2 changes of colors. So say we try to go green, brown, green. You have to orthogonally connect the green region, but then that will break the brown region into multiple regions, which is not allowed, right? We have all the greens are orthogonally connected, and all the browns are orthogonally connected as a region. So that's why if you have more than one change of color here, sorry, if you have more than 2 changes of color on the edge of a yin-yang shading, it's not going to work, because you'll have to basically connect 2 of the regions, and then that will break the other region into multiple regions, which is not allowed. So we know to get to these cells, you could have 1, but you can't have 4, 3, 2, and 1 are never going to be able to form a branch going this way. So therefore, it cannot be broken up. It has to be all one contiguous green, and then we have potential brown here, potential brown here. So these are all green. Which is interesting then. We cannot have all greens here. So at least one of these is brown. But the thing is, to get to this level, we know that these cannot be brown. Only 2 of these digits can be brown, because you have a 4 and a 5, which you can get to from the branches. So 1, 2, and 3 are not going to be brown here. So 2 out of these are not going to be brown. Well, if we have something like brown here and brown here, the problem is this is going to have to be a green area here, because branches can't reach that way. So for the 4 and the 5, you're going to have the brown essentially go something like this. But that's not going to work. So I think the browns in row 2 then have to be here and here. Because otherwise, if you don't have something like that, you're going to have, you're going to have to go brown, brown here or something like that. You can't go brown, brown here, because then these would all be green, and there would be 2 by 2 area that's all green. If you go brown, brown here, or brown, brown here, or brown, brown here, then these would all be green. So, okay, what are the possible combinations? You have brown and brown next to each other, but then we know these are both green. That's a 2x2 area that's all green. If you have brown, brown, that means these are green, which means you cannot have a brown there because all the brown has to be one contiguous area, and this is blocked off by brown from brown. So therefore, this 2x2 area would be all green. Same with this. If you have brown, brown here, these are both green. 2x2 area that's all green. Brown, brown here, these are all green. 2x2 areas that are all green. And that works this way also. So it must be that these two cells are the browns. So we have brown here, brown here. The rest is green, which means this must be green to not be orthogonally connected. So this has to be 4 and 5. We have 4 and 5, which means the remaining digits in this row must be 1, 2, and 3. Let's see. The brown has to be orthogonally connected, so this must be brown here. This must be brown here. We're gonna have to have some swap here. We don't know where. There's going to have to, so this cannot be 5 here. Because it would have to be, or brown. So it has to be, this has to be then 3 or 4. It can't be 1. 1 is not going to be smaller than, or bigger than both of the cells that it goes to reach to there. This can't be 1 or 2 for the same reason, right? If we try to go brown, brown there, this has to be at least 3. So this is then, we know this is 4, this is 2, this is 3. 4 eliminates 4 here, so it's 5, which makes that 4. We know 5 cannot be any of these cells because it would be able to increase from that cell to that any other cell. This cannot be reached because it has to go brown, brown to be increasing. So this must be green. Since these are all green, it cannot be a branch going from the 4, so 5 has to be one of these two cells. This can't be 5 because of 5 in the column, so 5 has to be here. This can't be 4 or 5. We have no 3, 4 there, so this must be 1, which makes this 5. So this is almost certainly going to be brown because it's going to be able to be reached by either of these cells. So this is brown, and this must be green. So this must be brown also to be orthogonally connected. This must then be green. This cell has to be smaller than all 3 of these cells. So it cannot be a 4 here. Well, it couldn't be 4 anyways. This can't be 2. This can't be 1. No 1 or 5. This is 2, 3, or 4. So if we have, well, we could have a 1 there. This cannot be 1. If that were 1, that would force this to be 2, and 2 would be greater than 1, so therefore the root would have to go that way. So we know this goes from here to here. This goes from here to here. This green must orthogonally connect, so this is green. So this is also green, which means this cannot be... Wait, there's no other place for 5 then. How does this work? This can't work. Because this has to be 5, which is going to be greater than one of these two digits. Huh. That's a problem. Um, hmm. Maybe hmm. Maybe we don't have to draw them in, if that's the case. Right? And in which that case, huh. Well, this still has to be 4. So we have to have 4 there, which makes that 5. I think it has to be that case. This is 2 to be in a 1-to-2 ratio. Well, then we don't know if 5 is one of these if we specifically don't draw them in, right? Because these have to be green. Okay, I don't understand quite the rules of the tree growth. I guess it doesn't say, it says from one of the more roots, draw brown thermal branches along which digits increase. It doesn't say that just because a digit increases, you have to draw the thermal branch, right? So I guess that could be the case. One of these must be 2 then, to extend from the 3, which we already knew, which means one of these is 1. To be able to go from the 2 to the 3. 4 has to be able to go to from the 3 down to the root. So this would be 3. I guess it could be 3, 2, 1, maybe, or 3, 2, 1. But then the problem with that, okay, so one of these is not going to be able to reach. One of these has to be green and the other one blue or brown. So one of these is green, one of them's brown. One of these is green, one of them's brown. Yeah, I guess what we have to do then is something like that. Though, yeah, it cannot go from, this is 1 or 5. So either it's going to be 1, which is not going to be a reach from the ground, or it's going to be 5, which can't then go here. So this is definitely going from branch there. You could potentially have 4, 3, 2, 1. That is potentially possible. This can't be 4 because of 4 in the column. Remaining digits are 1, 2, and 5. 1, 2, and 5 in column 2. We do know 1 has to be one of these to go to the 2, which needs to go to 3 and 4 there. So this cannot be 1. So we have 2, 3, 4, 5 here. This cannot be 4 or 5 because of 4, 5 in the column. This is 1, 2, 3 left. Yeah, I guess the tree growth isn't that you have to go from... If you have a 4 to a 5, it has to necessarily have a branch. It's that you draw these branches, and they must be increasing from the root. Remaining digits here, 1, 3, 4, 5, 1, 3, 4, 5. Okay. We have to connect to here. This could be brown here. But this has to connect some way. I guess it could technically do that. But then this doesn't work as a branch, right? If we go that way specifically, you go 1, 2, 3, 4, 5. I guess it could work that way. But if you go 1, 2, yeah, and I guess it could be 3, 5 there. That's interesting. If this is 3, this is 1, and this is 5. The problem then, so if this were 3, that would be 1. It would never be able to go from branch to there, because that's 1. So it would not be increasing. And then this would not be, you'd have this be brown, trying to go this way. So this can never be the way that it goes. This can't be 3, I guess, is what I should be saying. And if we try to go around this way, 1, 2, 3, 4, the problem is it needs a way to directly connect to there. And that wouldn't be the case if this were 3. If this is 3, this is 1. You cannot increase from this cell to that cell. You can't get to this cell as a branch because this 1 is smaller than everything else. And you can't get to here because that's 3. So this can't be 3. This has to be 3 here, which makes this 2, which makes this 1. So that eliminates 1 in the rest of the row. This eliminates 2 in the rest of the row. We can't have 3 here. This must branch to here, which means it must go from the 1 there. Or the 2. It could go 2 and 1. But either way, it has to go from the root. So this must be smaller than 3. Well, it can only be 1 then. So this is 1, this is 5. There's no 5 here. This is brown. To get from 1 to 2, it has to go this way. So this is 2. So it must go this way, this way, this way. This can't be 1. It's 4 or 5, but this must be green. Yeah, I guess it just must be that you can't have... You have to draw the roots. And it's not that if just because it's greater, it has to be... We have to draw the roots necessarily. So this can't be 2. This is not 1, it's 3 or 4. 1 eliminates 1 here, so that's 3, which eliminates 3 in the rest of the column and row. No 3 there, no 3 here. We have a 1-2 pair and a 1-5 pair here. Wait, that doesn't work. Because we're guaranteed a 1 here, we're guaranteed a 1 here. Huh. Oh, this doesn't have to be a 3 here. Because it could go somewhere else. So because of that, we know that this cannot be right. Okay, so that's actually incorrect. So this, it just has to be greater than 1 digit in row 2 and 1 digit in row 1. Which means it's at least 3. So it could be, this can't be 1 or 2. It's 4, which makes that 5, which makes that 4. But this actually could be 5 here. And we showed that it has to be 5 there. Because the problem is, so this can't be 4 here. No 4 here. The problem is if we make that a 3, this can't be 4 or 5. 2 can never be on a branch because it's not going to be greater than 2 other cells or 2 other digits. Interesting. Yeah, so what we're going to have to do is basically make sure... Right, we still have the same problems here, right? If this is the 3, that forces this to be 1, therefore it's green. but then this would be brown trying to go that way. But then you'd have green trying to connect here, and this brown would not be orthogonally connected to the rest of the browns. So that's why this can't be 3. If this can't be 3 because it can't go 4, 3, then to the roots here, I guess it could be 4, 3, 2, 1. But the problem is, if you have brown, brown, brown here, this would have to be brown. This would have to be brown. I guess that is potentially possible. I'll have to think this through more, but this has to go 5, 4 that way. You potentially could do 3, 2, 1 there. Either way, that forces 1 to be here, right? Because it's 3, then this can't be 2, and it has to be less than whatever to be able to go brown, brown here. Or you could go brown, brown, brown. And then... Right. Either way, to connect as a branch, it has to go 4, 3, 2, 1. And if it goes 3 there, the problem is that this could not be brown. It would be green because it's 1, and it's not greater than any of the digits that could be here. And then to try to connect the greens together, that would necessarily force the browns to be 2 separate areas, which is not allowed. So we must go 4, 3, 1, or 4, 3, 2, 1 this way. So this is guaranteed to be 1 here, which makes this 3. This is not 1. This is 4, 5. That's 4, 5. 3 cannot be either of these. 1 has to be one of these two. 1 has to be one of those two in row 2 and 3. So that eliminates 1 in the rest of the column. So this can't be 1. This can't be 1. We have to go from 1 here to 2. And it can only go diagonally that way, so this must be 2. This is 4. So this is the brown going that way. So this is brown here. This 4 eliminates 4 here, so that's 5. Since this is brown here, these must both be green. So this is green, this is green. That means this must be green that way. So this has to be the 3 that it corresponds to the 4 there. Okay. This can't be 4 or 5. It's 3, which makes this 1. So, and this can't be 3. No 3 here. So this can't be brown. It must go around here. So brown has to go here. It must orthogonally connect it there. So that's brown. So therefore, this does go 1, 2, 3. And it has to go branching that way. Here, it must go branching that way and that way to be able to form the tree. So this must be greater than 1, 2, or 3. This must be greater than 3, so this is 5, which makes that 1, which makes this 2, which makes that 1. 5 eliminates 5 here, so it's 4. This must be greater than 3, so this has to be 4. I guess technically it could branch that way. Yeah, and it's just that you don't branch specifically that way. So then this is 3 or 5. This can't be 3 because it's 3 in the column, so it's 5. That's 3, which makes this 5. That's 3 in the corner. We celebrate because we're close to solving it. This is 3, and that's 2. I would say that these rules are kind of unclear, but I guess it's fine. I would prefer it basically saying just because a digit is larger than another digit does not mean that it has a branch to it. I don't know. Maybe that's sort of implied. But it's kind of unclear. Well, I don't know. Maybe I just read too much into it. Yeah, so that's the solve. Kind of, yeah, as I said, I got the wrong impression. Maybe that's just something of an assumption that I make, which wasn't good. I don't know. It's an interesting concept, but at the same time, I do feel that there was, I don't know, there's some, and as I said, it might be my own just misinterpretation or misassumption. But I interpreted that basically anytime you had a larger digit, it was going to be part of the branch. But maybe that's just something that on my end that I'm missing. Anyways, I hope you enjoyed this solve, and I'll see you next time on Frank Puzzles. Take care.